Hi everyone, welcome to Wednesday, day 3 of the workshop. We're very happy to have you all here, and I'm very excited about the lineup of speakers that we have for today. And kicking us off for today, we have Evelyne Hubert from INRIA, and she's going to tell us about algorithms for fundamental invariants and equivariants of a finite group. So thanks a lot.
Thank you so much. I'm enjoying my time here, so thanks for the organizer for putting up the program. So during the first week, it really was bad because I kept hearing, you don't want to compute the invariants, it's way too hard. So here is my title, I have a bit of a contradictory spirit. I'm nonetheless going to restrict myself to finite groups, which makes it maybe a bit easier. But what is really new in this approach that I will be describing, do I speak too loud? Do I need the microphone? Nobody complains? It's good. So what will be really new in this approach is that we are going to compute both the invariants and the fundamental equivariants at the same time, which usually equivariants there come as an afterthought. So that's really the new idea that will be at the heart of this paper that I'm presenting. It's a paper that is already published with my former PhD student Eric Rodriguez-Bazin. And importantly, it's a paper that is dedicated to Karin Gatterman, who was a pioneer in symmetry in algebraic computations. And she was certainly one to recognize that equivariants were just as important as invariants. All right, so starting off, I will spend a good time motivating why we need equivariants and kind of defining things. So some of the material will be boring to some and maybe hopefully useful to others. The motivation is really how to do symmetry preserving, symmetry exploiting computation. And there is a package I'm trying to develop, Psycho. So let me first say that what is symmetry for you? This is a bit silly. So this is a running example for all my talk. I'm going to take the symmetric group on 3 elements. It fits on the slide, that's perfect. So it's a group of order 6. It has 2 generators, S1, S2, and with some relationships which are given here. And maybe I could get a pointer so that I can play with the light and get you all psyched up with the little movements, wiggling movements. And here, do you think? Yes. I guess I need to, no, this is not going to work on the, can I just use the pointer? Yes, if I put it on. Yes. You can also view this group as the group of symmetry of a triangle. So now the generators, they are the reflection according to this line and this line. It's the symmetry of a triangle. So that means that you have a representation of your group, which is a 2-dimensional representation. It's given by matrices. And then probably something that is mostly used is the representation in dimension 3, where you permute the coordinates. So here the first generator permutes x and y, and the second generator permutes y and z. All right. Okay, so on this example, we all know what are the invariants. So let me point out, because I'm going to use this notation several times. This 2-dimensional representation is tau. That's the representation, that's the symmetry of a triangle. And the permutation representation of a coordinate in R3 is rho. So the rho invariants, you all know them, because are these elementary symmetric functions. And what we mean by that is that they generate the invariant ring. Any invariant can be written as a polynomial in this H1, H2, H3. So now if you look at the row tau equivariants, these are now row vectors of polynomials. So the dimension is 2 because tau is dimension 2. And now this is a bit of a different condition as this one, where for H to be invariant, it has to be that when you compose it with the permutation, then you remain the same. Here, when you compose your polynomials with the permutation, what you obtain is the same polynomial matrix multiplied by 2, S being an element of a group. So it's not hard to think that these equivariants, they form a module over the ring of invariants. And this is a finitely generated module. And in this present case, for this action of rho and tau, the equivariants, the generating equivariants are these two row vectors, one in degree 1 and one in degree 2. So this was introduction to equivariants and to symmetry. I'm going to explain why these equivariants are kind of interesting from a symmetry, from an algebraic computation point of view. There is a great deal of work in applications about, in applied algebraic geometry, about checking if a polynomial is positive. It's related to optimization and a bunch of things. So there is no, there are certificates. And one of the certificates is that the polynomial is certainly positive if it is a sum of square. So that's a sufficient condition. So that's what you try. So what you do here, so you have this polynomial, you take a basis, so if it's a sum of square, it should be the square of polynomial of degree 2. So you take a basis of degree 2 polynomials, and you try to write your polynomial as a scalar product with a symmetric, definite, semi-definite positive matrix with this other set of monomials. Okay? But now, this matrix is absolutely not unique, so you have to call on semi-definite programming to find something that gives you this certificate. And the bigger the matrix, the worse. The more difficult. So there's a lot of research on how to do things more efficiently by exploiting the structure of the polynomial by just trying to figure out to be positive. So here in this case, guess what? It's a symmetric polynomial. And what you would want is that, maybe symmetric polynomial, maybe all sum of square of, if you are both sum of square and symmetric, maybe you are sum of symmetric polynomial, sum of square of symmetric polynomial. But that's not true. So what is true was came in this paper of Gatterman and Parillo, is that you can, if it is symmetric and it is a sum of square, then you can write it as a sum of square of invariants, but also of all the components of some equivariants. And so the way to look for that is to take what is called a symmetry-adapted basis of, again, the degree 2 polynomial. So here these are the block of invariants. So that's the degree 2 invariants. Remember, these are the elementary symmetric functions. Then this is a block of the equivariants. So this is the degree 1 multiplied by the invariant of degree 1, and then the degree 2. So you notice that here, this symmetry-adapted basis is not exactly the two equivariants put next to each other. You have to shuffle them together. So once you look, if you have written things in a symmetry-adapted basis, the thing is that this symmetric matrix that you're looking for will have a block structure. It will have a block structure of first here something of a 2 by 2 matrix that corresponds to the invariant block. And here you will have two identical matrices that corresponds to the block of equivariants, of two-dimensional equivariants. And so that's really the, you're making a lot of economy, because in the end you have only two by 2 matrices to check for positivity. I'm not liking that. Hello, it's me. All right. So this, I mean, as I'm showing here, the equivariant allow you to form symmetry-adapted bases, and symmetry-adapted bases are really the core technique to use symmetry to reduce algebraic computation. And it's always of this flavor. You block diagonalize a matrix. So forming this symmetry-adapted basis is personally my major motivation to go after invariants, equivariants. But you and they are used in this flavor in several works, in global optimization, in approximation, in combinatorics cryptography, but also very much so in physics and chemistry, where you express the potential of the electricity. Well, you know, some vocabulary that would be very impressive, but that I wouldn't perfectly understand.
Is the motivation here to get a non-negativity certificate for this kind of symmetric polynomials?
So I'm using this positivity to illustrate how symmetry can be exploited. But this is not really my work, and this is not what I'm going to speak about. I'm just explaining what I'm aiming at is computing symmetry-adapted bases. Okay, let me say it again. What I'm aiming at is computing symmetry-adapted bases, so that all this other work that want to exploit symmetry do have a tool to create these symmetry-adapted bases. Is that?
Yeah.
Yep. Make myself clear. All right. So there are quite a few motivations outside of this more personal motivation, and motivations to look and compute equivariance. So first of all, I mean, there are many in practice. There are quite a few dynamical systems or even PDEs that have some symmetry. And so, for instance, this old model of a neural network, as you will see, it is the right-hand side is given by an equivariant. If you switch x1 and x2, you actually obtain the second equation. So looking at when you, and this happens a lot when you have, you know, several items of the same species. You write the equation, but actually, you know, x1 and x2 can be interchanged, etc. So when you, so what these papers that I cited address is the fact that if you have an equivariant system like that, you actually have a lot of equilibria, because you know you have the if you have one equilibria, all the permutation of its coordinate is also an equilibrium. So that's really tough on Grosvenor bases or resolution of polynomials. So they develop some specific scheme to kind of attack these problems. But what I mostly want to say on this slide is that sometimes when you're trying to create a model, so for instance in mathematical biology, you know some features, some qualitative feature, and symmetry could be one of those qualitative features. So what you want to do is create a dynamical system with as few parameters as possible, but that reflects this symmetry, this qualitative feature. So if you want, for instance, here, this is again the symmetry of a triangle. you kind of know that your system is going to have this symmetry for I don't know what reason. And the thing is that the way you have to model it is then by taking the right-hand side to be an equivariant. So you have to know the equivariants, and then you can just put some linear combination of them to obtain the symmetry. So that's another motivation to compute equivariance, a very serious one. But on which I haven't worked myself. All right, so this was the end of motivation. I've explained what are equivariants. I'm going to say more precisely what are fundamental equivariants. I've already also mentioned symmetry adapted basis, and I'm going to show that there is a kind of there is a link between the two. That is, one uses the other, and the other uses the other. I mean, it's kind of an exchange relationship. You give me up to degree d some symmetry adapted basis, and then I gave you the fundamental invariant, and this fundamental invariant give you the symmetry adapted basis for the higher degree. So that's the idea. So let me, this is again the same slide. I said it was the running example, and it's, you're going to remember this slide. So again, this is my group of order 6, and the only thing I'm adding in this slide is that in this representation here, as you know, there is a line that is invariant. So that means that your representation can be cut in two invariant spaces, orthogonal to each other, actually. So that means this representation is irreducible. The complement of this line is actually going to be this symmetry, this representation. And this representation is irreducible. There is no invariant subset, invariant subvector space. So you have a notion of irreducibility of the representation. And lucky for us, I mean, that's you have finitely many inequivalent representation, irreducible representation. So a finite group has finitely many representations, irreducible representation. So from now on, I'm going to omit very often that I start with a representation in dimension n over, I like R, but C works too. R1 to RT are going to be my irreducible representation, a finite number of them, with the convention that the first one is the trivial representation. And then the nth representation is going to be of dimension NL. Okay. So what I'm going to be considered as a basic equivariant is an a row RL equivariant, where RL is an irreducible representation. So it's a row vector of dimension NL, such that you have this equivariant property that we already see. So the fundamental invariants and equivariants of my title consist exactly of the generators, hopefully a minimal set of generators of the ring of invariants, and the generators, hopefully minimal too, of the invariant ring modules, I mean the modules over the invariant ring that correspond to each irreducible of equivariants that correspond to the irreducible representation.
So for each of those, you just need one vector, since there's.
Sorry?
So do you need just one vector for each of the irreducibles?
No.
You sometimes need more.
Yes. So in the example we've seen, there were two vectors, one of degree 1, one of degree 2. So this is again, so I'm completing the pictures that we've already quite explored so far. So this is again the, so here my representation is the permutation of a coordinate in R3. what are the irreducible representation of S3? We've already seen two of them, the invariant one, the trivial one, the two-dimensional one, which is the one of a triangle, and then the last one is a one-dimensional representation, which is the signum of the permutation, of the determinant, if you want. So here, we know the invariants. We've seen the equivariant for the two-dimensional representation, and for the last representation, it's indeed only one equivariant, but still it's a module over the invariants. All right, so that was, I defined this fundamental invariant. The goal is to compute them so that we can compute higher degree symmetry adapted basis, but to compute them, we are going to use symmetry adapted basis up to a certain degree. All right, so that's what I'm going to try to explain. So I'm explaining symmetry adapted basis. It's a concept that has been used a lot in physics, chemistry, also in, well, many places.
Can I ask a quick question? So in the example,
It doesn't have to be quick, we have time.
in the example, those were all free modules over the brain. So are the module of the equivariants typically free modules, or is this just an artifact of that example?
It is. So yes, I was going to point it in later slides, but you're right. I mean, this was an artifact. It's a very nice property of that is only for reflection group. For reflection groups, the fundamental equivariant modules are free, and they are generated exactly in the dimension of the irreducible representation. So, thanks. I can drink a cup of coffee.
Is it also true for the Shepard-Todd complex reflection groups?
Yes, it is. All right. Thanks for your break. Okay, again, I have my representation row. I have of a group, and then the irreducible representation. These are all given to me. That's my assumption. And so, because rho is reducible, there is a way that I can find a change of basis so that my representation is going to be block diagonal with first a lot of diagonal of R1, of trivial representation, and then a diagonal of R2 and a diagonal of RT. And the number of times each representation is repeated, it's called its multiplicity. So this basis, this basis that allows me to diagonalize my my representation, I will give it a name. I mean, I'm going to decompose it as such. For each irreducible representation, there will be a set QL, and this set QL is made of a row vector of vectors, if you want, but I'll put them under brackets, each of size NL, and whose span a vector space, and the rest that is invariant under the row representation, and on which the representation is exactly RL. Okay? So I have this basis. So this is the basis I'm going to call symmetry adapted basis in this example, but it's not exactly that. Actually, you need to, as I said it quickly earlier, to get a symmetry adapted basis, you need to shuffle things. You need to put things a bit together. Anyway, there is a bit of an order to do, reordering to do. But for this talk, it's more practical to keep this notation. So the symmetry adapted basis, can be computed, but with projection operator, that kind of generalize the Reynolds operator. And this is very well, beautifully explained, in chapter 2 of Sayre's book on linear representation of finite groups. So it's really linear algebra. Computing a symmetry-adapted basis is put a projection, compute the basis of a projected space, blah, 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 blah. Don't mix up the indices, and you get there. And so the interesting part of having a symmetry-adapted basis is that if you have so many things which are, as I kind of already tried to explain, many things that have symmetry in some sense, it is expressed by an equivariant map. So for instance, if you have an equivariant map from a vector space U with a representation mu to a vector space V with a representation V of the same group, this is equivariant if you can commute the permutation with V. And if you choose for U and V symmetry-adapted basis, like we've done just before, then your the matrix of phi of phi, T, let's say phi, is going to be block diagonal with only one block of phi1 that corresponds to the irreducible representation, and then for each other representation, there will be one block, the size of which is the multiplicity of the representation. But then the same block is repeated NL time, NL being the dimension of the representation. So you're block diagonal, and many of the blocks are repeated.
So how much of this is related to the sort of Vedder decomposition of the group ring?
Sorry?
So the group ring is a direct sum of matrix algebras. Is this coming from that or related to that? What reach you're up?
Yes, in some way, but I can't tell you now.
Okay.
So this symmetry-adapted basis that I introduced, this was for any vector space. Now we're coming back to the vector space of homogeneous polynomials. So I have a representation in n space, and then that induces a representation on the polynomial ring that leaves all the spaces of homogeneous polynomial invariant. So the action is by composition. So that means that this vector space can be written as can be decomposed into these blocks, isotopic block we say, but that each corresponds to an irreducible representation. And now these blocks, they have a symmetry-adapted basis in the sense that we gave. They are the components of these row vectors that I kind of signed up. And now, these row vectors, they are actually equivariants. This is polynomial. Okay. So, what am I writing here? So here, if it's kind of a symmetry-adapted basis decomposition, it is all kind of given by equivariants behind the scene. So these blocks, which are the symmetry-adapted block, they are also, with some reorganization, the equivariant, the degree D part of the equivariant modules. Hello. So the contribution that we're going to make, the goal to which I'm very slowly going to, is that I'm going to compute symmetry-adapted basis of a vector space of polynomial up to a certain degree with the projection operators that I flashed at U. And from there, I will be able to isolate the minimal generators for the fundamental invariants. And once you have the once you have the generators for the fundamental invariants, any other equivariants can be obtained by linear combinations. So here we go. Algorithms. Plenty. So let me start by saying what used to be the, so we had a lecture by Derksen in the first week about computing invariants. He focused, I would say, more on computing reductive invariants of reductive group of positive dimension. But so there was quite a lot of work that went in a slightly different direction about finite groups before or in between or at the same time. So it's all starts with the idea that computing invariant is not theoretically hard. You have this Reynolds operator, which is a projection you take of the polynomial ring to the ring of invariants. So that's this P1, what I've noted as P1 here. So, you can start, you can take the degree 1 polynomial, the basis of degree 1 polynomial, compute the Reynolds operator, so you find all the degree 1 polynomial invariant. And then you go to degree 2, find all the polynomial of degree 2, find all the invariants of degree 2. And you know that it will finish, but the question is, what is the termination criteria? Okay, so that's the difficulty, is the termination criteria. So in this, so here I'm citing quite some books where things are explained. So in this first instance, what's happening is that to compute these invariants, you kind of remove the ones that can be obtained from the others, and then you take at some point, you compute the Hilbert basis of the algebra that these invariants you have generate, and and if this corresponds to the Hilbert series of the invariant ring, which you know by Mollien's formula, then you're done. Okay, that's the first idea. The second idea that is also explained, so in this, that is more developed in these two books, also Bibles, Bibles, and is that you first start by computing a homogeneous system of parameters. And there is a criterion for that, so that means you compute some invariants that are algebraically independent, so this is something you can check, and whose only the ideal of which the zero set is only 0, is restrictive. So that's the criteria. So you go and you try different things. Once you have that, then you can reorganize your Hilbert series of invariant ring according to Mollien's formula to read what should be the secondary invariant, the degree of a secondary invariant, and then woof, you just go and compute this degree D, this degree invariance. So that's it. Then way later, so we saw, Derksen kind of explained his idea of computing the invariants. I mean, he explained it mostly for reductive group, but it also works for finite groups. It kind of uses the Hilbert ideal, and I will define what is this of a null cone ideal in some way. But then in this, now this is a paper that is using things very differently in a very more efficient way, actually. So in the second edition of the Bible book by Derksen and Kemper, hello, this is recognized as the best, as the fastest algorithm for computing invariants for finite groups. Okay, now the computation of equivariants basically was completely dismissed from this scene, because the way it was dismissed is that if you look for the Rho-tau equivariance, you can actually see this. It's actually you can identify this equivariance to a submodule of the bigger representation Rho plus 2. And so it's only in the book of Geiterman where she goes and computes only what is needed exactly for this equivariance. But that's really a computation you need to do after having computed the invariance. All right. So what the algorithm will be presented as some kindred spirit with King's algorithm. We discovered that after the fact. But the termination criterion is very different, and King's algorithm only does invariant, and we will be doing also these fundamental equivariants. So how did it come to be? It's at some point I was reading, catching up on reflection groups, and I realized that the work I had been doing with Eric on symmetry preserving ideal interpolation could apply completely directly to compute the invariance and fundamental equivariance of reflection group. It was just a direct application. It was fantastic. Of course, I mean, reflection group, lots is known about their invariance, so who cares? But so some earlier work also could be used to, if you know some the primary invariance, then you can compute the secondary invariance and all the fundamental equivariance with this other work on symmetry preserving interpolation. But I'm not going to speak about that. So then we generalized everything. And I'm going to tell you how to compute simultaneously the equivariance and the invariance. And I'm first giving you the first key concept that come in, and then the key ideas. So what I've been calling the Hilbert ideal, sometimes it's called the null cone ideal, but in the finite group case, I mean, the null cone is just 0, so it's not that interesting. So it's the ideal that is generated by all the positive degree invariants. Okay, this ideal has a long history. It appears already in the seminal paper of Hilbert, where he showed that a set of invariants generates the ring of invariant if and only if it generates this ideal. Okay. Now there is another concept, which is the covariant algebra. So that's the quotient of the polynomial ring by this ideal. And because, so it's a C vector space, and because the group is finite, this is a finite dimensional space. So if you take so if you think of this ideal as a vector space for a minute, and you take its direct complement, maybe orthogonal complement, then this basically is the quotient. And so that's what we're going to do. We're going to choose such a complement that is invariant, like for instance the orthogonal complement. And we are going to, because it is invariant, we can have a symmetry adapted basis of it. And as a consequence, because our polynomial ring is graded and you have this Nakayama lemma, you can say that you actually have a decomposition of this polynomial ring into modules over the invariant ring, where you have to multiply by all these components that come here. And as you see here, I mean, it's not 3 modules, as you were pointing out, except for the reflection group here. So for a reflection group, this is also a direct sum. But for a non-reflection group, this is not a direct sum. But you have the plus plus. But the others can be shown to be a direct sum. So once you know that you have this decomposition, you know that this symmetry, this basis of the quotient, is actually a basis of the fundamental modules, fundamental equivariant modules. So that's the story. We want to know H, we want to know N, the Hilbert ideal. Its generators are going to give us the invariant, and the complement are going to give us, the symmetry adapted basis of the complement is going to give us all the fundamental equivariant. So the rough outline of the algorithm is the following. We go and compute degree by degree. So what we need to do is, there was the first talk of this, week was about, we explored all of the Grobner, border, Pomaré bases, which are all based on monomials. And this has no chance to preserve any symmetry. So we have to go for something a bit more intrinsic. And this more intrinsic thing is the notion of H basis that dates back to Macaulay. And that needs a lot of linear algebra. It's not the simple, Anyway, so we are going to compute degree by degree H basis of the Hilbert ideal. And at the same time, we're going to compute a complement in, say, in the degree D of the orthogonal. We're going to compute a symmetry adapted basis of the orthogonal complement. So at some point, because H is a zero-dimensional ideal, nothing new will come in the complement, and that's the termination criteria. At this point, you know that whatever is in H is a minimal generating set of invariants, and whatever is in the basis of the complement gives you the fundamental equivariance. Okay. So the basic computation, so I'm going to explain the basic computation the way it's not done, because you have to be a bit smarter for things to work semi-efficiently. Hello. So at degree D, we will start with this H, what we have computed up to degree D minus 1. We will prolong it. That means we're going to multiply by all the polynomial of complementary degree to get to degree D. Then we're going to, so we will obtain something. We will compute its complement. This complement is going to go into two categories, some things which are also invariant, and some things that are in the complement. So so that's the next step is to put this thing in H, and this thing to put it in the complement, and always keeping symmetry adapted basis things of things. So the way we do that is a bit more clever. We kind of exploit some equivariance of this map, and we use a lot of knowledge on the group, and we use also a switching lemma so that in the end you're not multiplying by any polynomial but only by invariance. So if there is a real request, I will go through the more detailed algorithm. But at the moment, until I hear cries in the audience, I will just show you two examples with pretty pictures to finish my talk. So this is, I'm still with this group, same group, because it fits in one slide. So, but now I'm going to look at my representation is the two-dimensional representation of on the triangle, but it's the same group, so it's the same irreducible representation. I run my algorithms, and because it's a reflection group, I obtain only 2 invariants. Okay. So that's the radius, and that's the fact that you're invariant under the rotation. Then the Q1, so if I look at the complement, Q1 is only going to be 1 because all my invariants are here. Q2 is 2-dimensional, has 2 vectors. It's a free module generated by these 2 things. Q3 is a single semi-invariant. And so you can you get a decomposition of your polynomial ring as a module over the invariant ring. And the different pieces are these ones. You have the invariant ring, the fundamental equivariance associated to the 1-dimensional representation, and the fundamental equivariance associated to the 2-dimensional representation. Last example. So now this is an even simpler example in some sense. It's the cyclic group C3. So now, I mean, because it's an abelian group, I mean, you have only 1-dimensional representation, but they are over C. But so what you can do is you can, because they are conjugate, these 2 of them, I mean, you have the trivial and the others are conjugate, you can kind of put them together to make it real and run the algorithm and with a bit of twist. And you see that here now you have 3 invariants. It's no longer a reflection group. You have this equivariant, 2-dimensional equivariant, and this decomposition. All right, and now this is the thank you for your attention page, but let me say, these are interpolation surfaces. These are interpolants for multivariate interpolants that preserve symmetry. So when you do multivariate interpolation, I mean, there's not a unique interpolant. So to preserve symmetry, you have to do something more. And so this was the starting point of this package cycle, and these are the examples I made. But over.
Thanks a lot. Questions?
I could ask a naive question. So on the slide where you had the Reynolds operator, so at some point you explained how to compute invariants. And so you said
Yeah, let me get there.
the literature overview.
Yeah, yep.
Yes, here it is.
Yes.
There. So you said for the first bullet you need to compute the Hilbert series of a monomial algebra associated to the invariants. Is that correct?
Monomial algebra. I mean, yes. I mean,
Do you think leading terms?
you actually indeed look. You actually look. Compute. So you take all your invariants, you compute the Grobner basis, and then you can compute the algebra. That's indeed. So you're also indeed looking at the monomial structure. I mean, it's how they do it. I mean, this doesn't sound very easy.
Okay, thanks.
I'm very sorry, but can we look at the page with the algorithm that we ran?
Wow. Yes, it's blue.
Roughly, can you say what's happening in the do loop without making us read too much? Just a high level, what's happening in these lines? Because
Yes. Okay. So I've computed HD minus 1. Okay. In the Hilbert, the H basis, where all the elements are homogeneous invariants. And I'm going to use complementary degree invariants to bring it to all to degree d. That's the prolongation. But only invariants. I'm prolonging only with invariants. And then I'm going to compute the orthogonal, so that means that this is everything I already know. And I'm computing the orthogonal complement of that in the space of invariant polynomials. So this is all Reynolds operator, checking complements, da 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 da. Okay. Now, for each L, for each piece that will compute a representation, so what I should be doing is computing the prolongation with equivariance of HD minus 1 and compute the complement. But, haha, that's where there is a very nice trick, is that this thing is actually equal to, if everything has gone right so far, is equal to the prolongation of what I've computed at the degree t minus 1 corresponding to this irreducible representation, and I just need to multiply by invariance to make it to the degree d. And then I have to compute the complement. So this is all QR decomposition. So now this complement goes into HD, and this complement goes to here. So, and I'm doing everything in two pieces. So the thing is that, yes, this. Yes, so you're just, so here when you're multiplying by invariance, some equivariance, and you multiply by invariant, you stay the same equivariant. So it's what's happening. And that's when you have no more complement here, that's when it stops.
Thank you.
Yeah, it was not that hard. Thank you for the question.
Oh, okay, go ahead.
You go first.
No, after you.
Because my question is a little peripheral.
Is a little what?
A little peripheral to the discussion. You discussed the Summit Square certificate as an example, the non-uniqueness of the Q matrix associated with the Summit Squares certificate for non-negativity.
Can you put your hands a bit lower so that I actually hear you?
You discussed the sum of squares non-negativity certificate earlier and the non-uniqueness of the Q matrix.
Yes.
The sum of square certificate obviously is not all polynomials that are non-negative in any degree, right? There's obviously a larger cone associated with that.
Yes.
What people do is they typically rotate the basis to trace out more of the positive semi-definite cone of polynomials, because the Q matrix they choose only gives them a small set of that cone. Do you think the symmetry adaptive basis that you're constructing, do you think that will address that problem and take out more of the positive semi-definite cone? You don't think so?
But you will compute it faster.
So relatedly, I wanted to ask about computational speed-ups. So like what size of finite groups are you able to run with, and what's the computational bottleneck?
Yeah. So one of my regrets is that my student who did the package, was very versed in computer science, and I should have asked him to implement in Singular. But it's implemented in Maple. So yeah, I think we managed to do up to non-variable and the octohedral groups, but with a bit of yeah. So.
And what's the bottleneck?
What is the bottleneck? Yeah, I think that the bottleneck is, very good question actually, and I think this really could be improved, and I think the GAP people should help, is the computing the symmetry adapted basis up to a certain degree. Mm-hmm. Yeah. And this is, yes, something that really could be improved by people who know a bit more on the topic. Yeah.
I see. I guess your algorithm is symbolic.
Yes. Yes.
I mean, could one do this also numerically?
So you see, the way I think of it is, for instance, when you are doing an interpolation, I think the numerics should come afterwards. I mean, you give the basis in symbolic computations, but you know that it's equivalent. So then, even if a numeric is a little wrong afterwards, you still have the symmetry, you see. So I feel it's really a pre-processing that has to be symbolic, so that the symmetry is there, for sure, and not kind of a wiggly symmetry.
Mm-hmm.
Yeah. But, I'm open to, this is my where I stand.
Thanks. Any other questions? If not, then let's thank Evelyne again. Thank you very much.